One night in 1669, a German alchemist named Hennig Brandt was searching, as he did every night, for a way to make gold. For some time, Brandt had focused his research on urine. He was certain the golden stream held the key. Tonight, his patience would at last be rewarded. He had boiled the urine down to a concentrated paste. Now he subjected it to intense heat. Was this the legendary elixir that would turn lead into gold? Alas, it was not. Brandt had stumbled on the element phosphorus. This is how the discovery of elements began, with people trying to turn the substances of nature into something useful or valuable. But people are naturally curious, so as they worked with these materials, they began to wonder, what is this stuff? What is the world made of? Thousands of years ago, the Greeks proposed that the world is actually made of just 4 elements in combination: air, water, earth, and fire. Today we know that matter actually comes in more than 100 distinct varieties, neatly arranged in the periodic table of the elements. But for most of history, matter was a profound mystery, a 2,000-year detective story in which people across the world were trying to identify the elements and figure out how to use them. It's an amazing story, filled with unforgettable characters. In this series, you'll meet 7 extraordinary scientists whose findings drove the search for the elements. So join me as we retrace the steps of these chemical detectives as they struggle to solve the mystery of matter.
Eh bien, chers amis,
Major funding for The Mystery of Matter Search for the Elements was provided by the National Science Foundation, where discoveries begin. Additional funding provided by the Arthur Vining Davis Foundations, dedicated to strengthening America's future through education, and by the following.
One of the first big clues in solving the mystery of matter came from the discovery of the most immaterial stuff you can imagine: air. Of course, people have always known about air. They could feel the wind on their faces and see its powerful effects in storms. What they didn't know was that there's more than one kind of air. That changed in 1754 when a young Scottish medical student named Joseph Black set out to find a cure for kidney stones. He poured acid on this chalky substance and trapped the air that came out. To his surprise, this air didn't behave like air at all. It was heavier than ordinary air and promptly put out a flame. Black's discovery of fixed air, what we now call carbon dioxide, was a turning point in the history of science. People had long known about liquids and solids. Now, suddenly, they realized there was a third state of matter: gases, of which air is just one example. Over the next 20 years, the exploration of this new dimension would transform our understanding of matter. After Black's discovery, British scientists quickly identified 2 more new gases: hydrogen and nitrogen.
And then in the early 1770s, that astonishing investigator Joseph Priestley discovers all sorts of new airs.
Priestley was a minister by trade, but also an amateur scientist, what was then called a natural philosopher.
He was a great dabbler in things and was constantly getting obsessed with new fields.
Fields like the new science of gases.
Priestley's style of science is very interesting. He's a kind of inspired forager. He's basically messing around with different things to see what will happen. One of the things Priestley did was to pour acid on everything. He collected those bubbles, tested them thoroughly, and discovered all sorts of amazing properties.
By messing around in this way, Priestley discovered 9 new gases, more than anyone else in the world.
He was very much open to chance discoveries. He would stumble across things and he would follow his instincts, and he was always looking for these kind of fortuitous accidents.
One such accident happened in 1767, when Priestley was assigned a new congregation.
They put him in a house that happens to be right next to a brewery, and this turns out to be an incredible stroke of good luck. Priestley, being the constant investigator that he was, would kind of pop over and see what was going on at this brewery.
Just above the vats of beer, he discovered a haze of carbon dioxide bubbling up from the fermenting brew.
And he decided he wanted to do some experiments with their beer. Well, fortunately, they said yes.
Priestley found that if he simply poured water from one glass to another over the surface, the water would absorb the gas rising from the beer. The result was refreshingly bubbly. By 1772, he had invented a better method, generating carbon dioxide and injecting it directly into water.
In the space of 2 or 3 minutes, I can make a glass of exceedingly pleasant, sparkling water. You can't tell the difference between this and natural mineral water.
Priestley had invented carbonation. Remember that the next time you enjoy a soft drink. But with this act, he also set in motion a series of improbable events that would soon overturn our understanding of matter. It began when a British doctor suggested Priestley's windy water might be effective as a treatment for scurvy, a disease that plagued sailors on long sea voyages.
Scurvy was a huge problem for the military during that period, and so the idea that there was this potential solution that it also happened to be a tasty beverage was appealing.
In 1772, Priestley addressed Britain's leading scientific organization, the Royal Society, and published a pamphlet describing his method for making soda water. He urged the British Navy to test the potential cure. Quick to pick up on this development was a defrocked Portuguese monk named João Jacinto de Magellan. A distant relative of the great Portuguese navigator, he was now serving as a French industrial spy.
Magellan is in the employ of the French government and is there basically scouting out the Royal Society for interesting items that he might be able to bring back to his bosses.
Sensing a potential military secret, Magellan alerted his handler back in France, Commerce Minister Jean-Charles Trudaine de Montigny.
Trudaine was interested in science, was a member of the French Royal Academy of Sciences, and immediately saw the possible value of this.
Trudaine, in turn, called on one of France's brightest young chemists, Antoine Lavoisier.
Et qui en est l'expéditeur?
Monsieur Trudaine de Montigny.
Monsieur Trudaine de Montigny.
Oui.
I know your precision when it comes to physics and chemistry, and I'm giving you a chance to be of service to your country. Please repeat these experiments and add your own observations. The value of these discoveries depends on our moving quickly. I hope you will not be long in getting this little work done.
Trudaine probably intended this politely phrased letter as an order rather than a request. Lavoisier really couldn't ignore it.
Though soda water would turn out to be useless against scurvy, this pointed suggestion by a government official acting on a tip from a Portuguese spy would set Lavoisier on the path toward his greatest discoveries. Born into a well-to-do Parisian family, Lavoisier had received a fine education and taken a degree in law. Now 28, he had joined a consortium that collected taxes for King Louis XV.
As a result, Lavoisier became a very wealthy man.
But his true passion was chemistry. Lavoisier spent 3 hours in his private laboratory before work every day and returned there after dinner, often accompanied by his young wife. Marie-Anne Paltz was the daughter of one of Lavoisier's business partners.
Antoine?
Oui?
She was just 13 when they were married, but bright, outgoing, and mature beyond her years.
Lequel est-ce que tu préfères?
Marie-Anne was virtually his collaborator. She knew English, learned chemistry, assisted Lavoisier in the laboratory. She was an extraordinary person. Had she lived in our own time, she probably would have become an outstanding scientist in her own right.
One of Marie-Anne's most important roles was to create the diagrams and illustrations that accompanied her husband's published work.
Marie Lavoisier's drawings give us the eyes to look directly into Lavoisier's laboratory. We can see the people, we can see the devices, we can see the arrangements of those devices. We can understand what Lavoisier did so much better because of what Marie drew.
Spurred on by Trudaine, Lavoisier eagerly studied fresh translations of Black, Priestley, and other British chemists who had pioneered the study of airs.
The work of these previous experimenters merely hints at what's happening when air is taken up or released by different substances. I shall review all their work, repeat all their experiments, taking new precautions in order to develop a coherent theory. This subject, I believe, is destined to bring about a revolution in physics and chemistry.
What made this new science of air so revolutionary was that it threatened to topple the reigning theory of chemistry, a theory inspired by the mystery of fire. Most chemists believed fire was due to some fiery principle that was given up during combustion. And all our senses seem to confirm this idea. Heat, light, smoke, all are released as the fire burns. By the mid-1700s, this essence of fire had been given a name: phlogiston. Phlogiston was the foundation of chemistry's leading theory for nearly a century because it seemed to explain things like metals and rust. When iron ore was heated in the presence of charcoal, phlogiston from the charcoal fused with the ore to form metallic iron. When the iron was exposed to air or water, the metal released its phlogiston as it rusted. Other metals went through the same process, forming the green verdigris of copper, for example. Ore plus phlogiston equals metal. Metal minus phlogiston equals rust, or what was then called a calx.
Only there was a problem. The calx was heavier than the metal. Even though phlogiston had left the metal, it's lost something and yet it was heavier.
The calx should weigh less than the original metal, but it doesn't. The calx is heavier than the metal.
Though many chemists were aware of this contradiction, they let it pass because phlogiston otherwise worked so well. But Lavoisier was really troubled by this because he was obsessed with the weights of his experimental ingredients.
Lavoisier was very careful to get very good instruments. He probably at one point had the largest and most complete private laboratory on Earth.
With my precision scales, imported from England at great expense, I measure the weight of each substance at the beginning and end of every chemical reaction.
Lavoisier was a master of this balance sheet kind of chemistry. Remember, he was a tax administrator by day. He knew a lot about accounting, and so this kind of ledger keeping was natural to him.
It is a fundamental truth of chemistry that the same amount of matter exists before and after each experiment. Nothing new is created, nothing lost. The whole art of performing chemical experiments rests on this principle.
Today we call this idea the conservation of matter.
When you carry out a chemical reaction, what comes out has to be exactly equal to what goes in.
The total weight must remain precisely the same. If not, there's an error somewhere.
He wasn't the first to assume conservation of matter, But Lavoisier applied this idea more rigorously than anyone had before. And it worked very effectively as a tool of discovery.
The power of Lavoisier's method would become clear in October 1772, when he set out to solve the riddle of why metals gain weight when they form calxes.
Common sense suggested that when things rust, they must lose weight. They fall apart, they become brittle and weak. Lavoisier was interested in actually measuring what happened.
He conducted his experiments in public, relying on a huge burning lens that focused the sun's rays to produce intense heat, while elegantly dressed bystanders watched in amazement. Lavoisier placed a calx of lead mixed with charcoal inside a glass vessel partially filled with water, then subjected it to the intense heat of the burning lens. The result was extraordinary.
As the calx changes back into the metal, it releases a large quantity of air. This air forms a volume 1,000 times greater than the calx it came from.
This startling finding suggested a radical idea. If air came out as the calx changed back into a metal, could it have gone in when the calx was formed? Could air be the reason calxes were heavier than expected? Lavoisier also found that when he burned elements like sulfur, they too gained weight.
There was then no doubt. I realized that the increase in weight occurs because a portion of the air is absorbed into the solid material.
He knew he was onto something very important. He knew that the element did not lose mass, it gained mass. It took up some part of the air.
I felt I must secure my right to this important discovery. So I deposited a note with the secrétaire de l'Académie to remain sealed until I was ready to make my experiments public.
He's discovered what seems to be evidence by weighing things that seem to flatly contradict what the phlogiston theory is predicting.
Despite what our senses tell us, both rusting and burning involve absorbing something from the air, just the opposite of what chemistry's reigning theory held.
It had been known for 100 years that metals gain weight when they become calxes, but no one had bothered to really investigate this anomaly. By focusing so intently on weight, Lavoisier had challenged the very foundation of chemistry, and he'd identified the source of that weight gain. Air was somehow involved.
But was it air itself or some part of the air? And if so, what part? The identity of the mystery gas eluded him for 2 years. He was still stumped in late 1774, but the answer would soon be delivered by Joseph Priestley. By this time, Priestley had begun to study something called the red calx of mercury. Mercury is a strange metal, one of just 2 elements that is liquid at room temperature. But like other metals, it forms a calx, a red solid that pharmacists of the 1700s used to treat venereal disease. Chemists had noticed something unusual about this calx. They could convert it back into metallic mercury simply by heating it. No charcoal, no source of phlogiston was needed. This was theoretically impossible. How could it be? The ever-curious Priestley wanted to know. So in August 1774, he obtained a sample of mercury calx and used his own burning lens to heat it with sunlight.
That reddish substance in turn decomposes, giving back mercury, but also a gas.
Priestley collects this air because he likes to test these gases and to see what properties they have.
If it were his old friend fixed air, the candle would go out.
But what he found about this air was it had quite extraordinary properties.
What astounded me was that the candle burned in this air with remarkable vigor. The flame was bigger and brighter than in ordinary air.
Something in this air seems almost better than normal air, which is very puzzling.
I was utterly at a loss. How could I explain this?
Eh bien, chers amis, buvons à la santé d'Archimède.
Dr. Priestley, have you been to the continent before?
No. This is my first time.
2 months later, on a visit to Paris, Priestley was invited to dine with members of the Royal Academy of Sciences, including Antoine Lavoisier.
J'ai récemment réalisé.
Priestley tells Lavoisier in his very broken French about his new discovery.
Avec le résultat très intéressant. I described this experiment at the table of Monsieur Lavoisier. I never make the least secret of anything I do. Le même air de plum rouge.
Everything that he came up with, every new experiment that he did, even when he wasn't sure what the results meant,
Qu'est-ce que c'est ce plomb rouge?
he was constantly sharing that information with as many people as possible.
Mais, à ma grande surprise, I also told them that it produced a kind of air in which a candle burned much better than in common air. Mieux que dans l'air commun. At this, the entire company, including Monsieur and Madame Lavoisier, expressed great surprise. I'm sure they cannot have forgotten these events.
Monsieur Priestley, êtes-vous bien sûr que ce n'était pas l'air fixe?
If you want, I can translate for you.
Ah, merci.
Are you sure that what you found was not fixed air?
Absolutely. But I'm not yet sure of what it was.
Lavoisier did not appreciate Priestley's style. He didn't think Priestley brought very much thought to his scientific foraging.
But Lavoisier was smart enough to recognize that Priestley was onto something and take that piece of information and go back to his lab to figure out exactly what Priestley had discovered.
Could this be the gas he was looking for? The one involved in rusting and burning? Lavoisier hurried to the local apothecary to buy his own sample of mercury calx.
Now, the tricky part.
Back in
Don't
England,
touch it. It's a
Priestley
surprise.
dithered for months on other projects,
Look what you can do.
unaware he was in danger of being scooped. Finally, it occurred to him, if this gas he had discovered supports fire, might it also support breathing?
Here we have one of the great discoveries in the history of chemistry, and the scene is kind of amazing. You've got this man and a mouse.
I put a mouse into a glass vessel containing 2 ounces of the air from the heated calx of mercury. If it were common air, a full-grown mouse would have survived in it perhaps a quarter of an hour.
15 minutes pass. 20 minutes pass.
In this air, my mouse remained perfectly at ease for a full half hour.
That's twice as long as any mouse has ever survived.
I began to suspect that the air into which I had put the mouse was better than common air.
He takes the same mouse, sticks it back under the glass, and sure enough, the mouse survives another 30 minutes in this strange new air. He realizes that something fundamentally different has happened. This air is some kind of super air.
I concluded that this air was between 5 and 6 times better, that is, more breathable than the best common air I'd ever tested.
He finally has kind of convinced himself this air must be safe to breathe if the mouse is doing so well. And so he gets up enough courage to actually try it himself.
It doesn't feel any different from common air when I breathe it in. But I feel peculiarly light and easy. In time, this pure air may be useful as a medicine or sold to the fashionable for recreation. Up to now, only 2 mice and I have had the privilege of breathing it.
As Priestley is conducting these experiments in England, across the channel, Lavoisier is basically going through the exact same experiments.
Lavoisier, realizing that this is essentially the key to the mystery, gets to work on it.
3. I found, much to my surprise, that this air had none of the properties of fixed air. A candle burned in it with a dazzling splendor, and charcoal, instead of just smoldering, threw sparks in every direction.
Lavoisier announced his findings with great fanfare at the 1775 Easter meeting of the Academy of Sciences.
All this evidence convinced me that this air is more breathable, more combustible, and more pure than even the common air in which we live.
And he gives it the name oxygen.
In announcing his findings, Lavoisier made no mention of Priestley's revelation over dinner 6 months earlier.
Now, Priestley is not a shrinking violet here. He hears about this and he objects.
He should have acknowledged that my account over dinner led him to try the experiment. One should not put one's scythe into another man's harvest.
I admit I was not the first to do these experiments. That claim goes to Mr. Priestley. But from the results, we have drawn diametrically opposite conclusions. I may be criticized for having borrowed from the work of this celebrated philosopher, but I trust that the originality of my conclusions will not be challenged.
Lavoisier was right. While it was Priestley who made the discovery, it was Lavoisier who grasped the implications of this new gas.
3.
Lavoisier was the only one who understood what was going on. Perhaps he didn't understand perfectly, but the moment that new element, which we call oxygen, was there, he picks it up and he runs with it.
Over the next 15 years, Lavoisier would show that air is not a simple substance, as the ancients believed, but a mixture of two newly discovered gases. That water, too, was a product of two gases, and that fire is not an element, but a process of combining with oxygen. Even the solid substances the ancients had lumped under the heading earth were now seen in a new way.
Metals like iron and tin and lead had been known for centuries. But in the era of phlogiston, they were thought to be compounds because they had phlogiston in them. Lavoisier had turned this picture upside down. He showed that by stripping away the oxygen from the ore, you got down to the simpler metal within. The metal, not the ore, was the element.
So all four of the ancient elements, air, water, earth, and fire, had been abolished, thanks to the discovery of oxygen.
Once you accept the existence of oxygen, the main difficulties of chemistry appear to evaporate. Well, if all of chemistry can be explained without phlogiston, in all likelihood, it doesn't exist.
For years, many chemists, including Joseph Priestley, refused to abandon the old theory. What finally won the day was the textbook Lavoisier wrote in 1789 to spread his new chemical theory. As it was adopted around the world, phlogiston quietly passed into history.
So the old chemical system has been essentially destroyed.
Though Lavoisier is often given most of the credit, it was really both these men, working in their very different ways, who brought about this chemical revolution.
They kind of needed each other in a way. For science to work, you need both kinds of scientists, right? You need the scientists who are great systematizers, and then you need the mavericks and the tinkerers who are going to open up new doors for discovery.
One of the doors Priestley and Lavoisier opened was a fresh way to tackle that old question, what is the world made of? It was clear now that rocks of every conceivable variety might harbor undiscovered elements chemically fused with oxygen.
People realized that if they could release oxygen from other substances, what was left behind might be some of these missing elements that everybody knew must be out there.
How many more elements might you find by stripping away the oxygen that like to bind to so many things?
Lavoisier's textbook included the first modern list of elements, 33 simple substances. Some, including light and heat, were later found not to be elements, but it was a start, and it served as a challenge to other chemists.
Now that they knew how to look for them, chemists began to ask, what are the elements? The question had never been asked before in exactly that way. And so the discovery of oxygen really served as a starting gun for a worldwide race for new elements.
All over the world, chemists and amateur collectors responded to Lavoisier's challenge, rapidly identifying 15 new elements. From Sweden to Mexico, Connecticut to Siberia, the discoveries kept coming, sometimes as many as 4 in a single year. And few things could bring a chemist more glory than identifying a new element.
Well, certainly, Lavoisier was one of the great masters of all time. In fact, his praise.
One of those who would soon be caught up in the hunt was a precocious chemist from the farthest reaches of England.
Pathetic ideas of phlogiston. Huh?
I've just met a remarkable young man whose talents I can only marvel at. He's not even 21 and has been studying chemistry for no more than 18 months, but he's advanced with such strides as to overtake everybody. Well, his name is Davy, the young chemist, the young everything.
Humphry Davy was the son of a simple woodcarver from the remote seaside village of Penzance, about a week from London by stagecoach.
Penzance is right down in the far southwest corner of England. And in some sense, it was the Wild West, right out beyond the influence of London and its institutions.
When his father died young, Humphry left school at 16 and took a job as an apothecary's apprentice to support the family. But he never lost his love of learning. He simply resolved to teach himself.
The same year that Davy's father dies, Lavoisier publishes his elementary treatise on chemistry. And young Davy reads this in the original French. He starts keeping notebooks from this very date, and there's a kind of intellectual explosion.
Chemistry arose from the delusions of alchemy only to be bound by the chains of phlogiston. But through the discoveries of Black, Priestley, and Lavoisier, it has now been liberated.
Davy started doing experiments right away. One of the things he did was to attack Lavoisier's theory of heat.
Lavoisier said it was a material substance called calorique. And Davy didn't believe this.
Davy thought that he could take on the great man. He thought heat was motion of particles, and he thought he could prove this if he could rub 2 pieces of ice together. So no heat would be coming in from outside, and the sheer friction would melt the blocks of ice. And that's what happened. To him and his contemporaries, the experiment was a convincing one.
Davy's findings, written up in his first published work, showed enough promise to land him a post closer to Britain's center of action, in Bristol, at the Pneumatic Institution.
So he leaves remote Penzance to become the assistant and then the director of this new institute. He's only 19, for heaven's sake.
The institution had been founded in the hope that some of the gases discovered by Priestley and others would prove useful in treating diseases. Davy's job was to make the gases and then test them.
I took just 3 breaths of the gas. The first produced a feeling of numbness.
One of the gases he tested was mostly carbon monoxide, the poisonous gas now found in auto exhaust.
He doesn't know exactly what it is, but he makes it, and he tests everything on himself. It's amazingly reckless, but it's also very brave.
He acted as if in sacrificing one life, he had 2 or 3 others in reserve. Some days I half despaired of seeing him alive the next morning.
And then he takes his pulse and he says, "I do not think I shall die." And he's ill for 48 hours, but he survives. On a number of occasions, he does nearly kill himself.
When you've got a career to make, and you're coming from a low point down the social scale, and you've got a long way to go, why not take a few risks? Get your way up to the top quicker.
The top Davy had in mind was the very pinnacle of science. On one page of his Bristol notebooks, he wrote his own name next to that of the most famous British scientist of all time.
Newton and Davy. So he has this sense that he and Newton can go at science together. It's not arrogance exactly, it's this tremendous drive, and he passionately believes that he will be a sort of Newton in chemistry.
I don't hesitate at all. The great master made a few mistakes.
All his life, that drive is there. Newton and Davy.
In Bristol, Davy sought out a group of literary men whose work would define the Romantic Age, including publisher Joseph Cottle and poets Robert Southey and Samuel Taylor Coleridge.
The assumption that heat is a simple substance. Is that what he called caloric? Precisely.
In looking at that group in Bristol, one of the things I think is wonderful, there was no gap between the writers and the poets and the scientists.
We can discover that the ice melts by friction alone.
Now, Davy, could not the melting have been caused by the temperature of the room?
That's a very good question indeed, one to which I have already answered. The air.
Every evening they're going out, they're writing letters to each other, going on walks together, and they're young men with a future. There's an extraordinary group.
In Davy, these romantic poets found a kindred spirit.
When we remove the ice from the point of friction, it refreezes.
A scientist who shared their sense of wonder at nature and yearned to reveal her mysterious ways.
Heat must, in fact, be the motion of particles.
There's an energy, an elasticity in his mind that allows him to seize on and analyze all subjects. Living thoughts spring up like turf under his feet.
Early in his research, Davy produced a gas one medical authority had warned was the cause of terrible diseases. He tried it anyway.
This evening I breathed nitrous oxide and experienced a thrilling all over me, more pleasurable than anything I have ever experienced. The objects around me became dazzling and my hearing more acute. Sometimes I responded by stamping my feet. Other times by dancing around the room and laughing uncontrollably.
As word of his discovery spread, many others, from steam engine pioneer James Watt to the king's own doctor, clamored to try Davy's laughing gas.
Coleridge and Southey both took doses of the gas. It was very much in keeping with this romantic time period.
He's invented a whole new pleasure. It makes you laugh and tingle in every toe and fingertip.
There was a certain amount of recklessness experimenting with drugs. Why not expand your consciousness?
It makes you strong and happy, so gloriously happy. Oh, excellent airbag. I'm going for more this evening.
Davy asked each of his subjects to record their impressions.
The first time I tried nitrous oxide, I felt a highly pleasurable sensation of warmth over my whole body. It was like the feeling I once experienced entering a warm room after returning from a walk in the snow. I felt no desire to move, only to laugh at those who were looking at me.
Davy wrote up their accounts in his first true scientific book. But just as he was finishing the book, Davy's attention was diverted by a discovery that would shake the very foundations of science. In 1800, an Italian named Alessandro Volta announced that he had created a new source of electricity. Up to then, the only sources of electricity had been lightning, which was very difficult to tap, and electrostatic devices, like the ones Priestley had used.
You could get quite spectacular effects in the way of flashes and bangs.
How are you doing that?
But you couldn't get sustained power. What Volta did was to establish that electricity was something that you could make a steady supply of, what we called an electric current.
Volta's device was incredibly simple. A sandwich of alternating copper and zinc discs separated by pieces of cardboard that had been soaked in salt water. But this voltaic pile, the first battery, electrified the world of science.
With the battery, you could now perform a variety of experiments that had never been possible before. And these experiments were done immediately.
Just weeks after learning of Volta's discovery, 2 British scientists used a crude battery like this one to split water into its 2 elements, hydrogen and oxygen.
The electric current was somehow breaking up the water into its components.
Even more surprising, the hydrogen collected at the negative electrode over here, and the oxygen collected at the positive electrode over here. Why would these 2 elements show a preference for opposite electrical charges? Intrigued, Davy set aside his research on gases, built a voltaic pile, and began doing his own experiments on electricity.
And it became Davy's big pursuit in life. What could this electric current do?
Volta has given us a key to some of the most mysterious recesses of nature. Till this discovery, our tools were limited. Now, the possibilities for chemistry seem boundless. It's like an undiscovered country, a land of promise.
Davy had just begun to explore that land when opportunity knocked. His book on nitrous oxide had caught the attention of the founders of the new Royal Institution in London, who were looking for a director for their chemistry laboratory.
And that book had such impact that it was read in London, here at the Royal Institution. It's very, very precise. It's measured, it's quantitative science, and they thought, this is the man we must get.
Still only 22, Davy set out on his next great adventure, leaving Bristol in 1801 for the city he called the great hotbed of human power.
When Davy arrived, his patrons seemed to be a bit taken aback to find this still rather raw country youth. But his natural eloquence must have come through and eventually charmed them.
One of the missions of the institution was to offer public lectures meant to stimulate an interest in science among the London elite. For this purpose, a theater had been installed in the institution's building on Albemarle Street. Davy started out as assistant lecturer, seen here helping his boss give a dose of laughing gas to one of the patrons. But with audiences shrinking and the institution's fortunes flagging, Davy was quickly promoted to the top job.
Nothing is so fatal to the progress of the human mind.
Determined to make the most of this opportunity, he set out to make each lecture seem spontaneous.
But to do spontaneous, what he did was prepare.
As to suppose that there are no new mysteries left in nature.
And he would read through, in front of his assistants, drafts of the lecture to see if it worked.
Who would not want to learn the most profound secrets of nature, to ascertain her hidden operations?
The moment Davy began to lecture, the audience is packed in.
Conquer. Science has done much for man, but it is capable of doing still more.
He had people absolutely lapping up what he was pouring out.
There were other chemists giving public talks elsewhere in London, but none held a candle to Davy.
He must have directed his bright eyes around his audience so that they felt really drawn in and mesmerized. And he would do dazzling experiments that he carefully rehearsed with his assistants the night before, so they always worked.
And people gasp, and they cheer, and they clap at the end of a demonstration. It's so brilliantly done. And these lectures became hugely popular. There were most terrible traffic jams outside the Royal Institution. Albemarle Street became the first one-way street in London because there were so many carriages bringing people to listen to his lectures.
He was young, he was handsome, he was eloquent, and there were a number of young ladies in the audience.
And they're all in the front rows making notes, but hanging on Davy's every word. Among the lecture notes in the Royal Institution archive are these little billets doux, little love letters, often signed with a pseudonym, and poems to him.
One of his female admirers invited him to dinner, noting, "Those eyes are too fine to be forever gazing over crucibles."
I have audiences of 400 or 500 people, many of high rank, and I suspect that some of them may become permanently interested in chemistry. This science is becoming the fashion of the day.
Davy's success as a lecturer and entertainer brought him wealth, prizes, and acclaim. But he was growing impatient. Giving popular lectures was no way to become the Newton of chemistry.
By 1806, he'd established enough of a reputation, and he knew that his work was supporting the Royal Institution. He could say, right, I've known your work for the last 5 or 6 years. Now I'm going to do my own work.
An invitation from an organization once headed by Newton himself gave Davy the perfect chance to show what he could do.
He was asked to lecture not to the Royal Institution, but to the Royal Societies, the top scientific group in the world. He needed to produce some dramatically original science.
With this goal in mind, Davy dived into the subject he'd been itching to return to ever since Bristol: electricity.
Up to now, we have studied electricity only in its most powerful form, lightning. But its slow and silent operations on the Earth's surface may prove more important.
From his early experiments, Davy had learned that an electric current could pry apart the hydrogen and oxygen atoms that made up water.
You can use a battery to unbond things and find out what the different elements are.
That gave Davy an idea. Could he use a bigger battery to tackle substances that were harder to break down?
This is something you can do with this new source of electricity. If a small battery gives you a small effect, build a larger one and you get a larger effect.
As the target for his experiment, Davy chose caustic potash, a substance derived from wood ashes collected in a pot. Chemists had long suspected it contained an undiscovered element, but no one had been able to break it down into simpler stuff.
He believed that if you could apply a charge to it in some way, you would discover something about its inner nature.
So Davy constructed a really big battery because he wanted to see whether potash could be decomposed into its elements.
Davy was thus able to use the resources of the Royal Institution to undertake scientific research, which had never been the intention of the founders of the RI.
But by the time he began the work, his Royal Society lecture was only a month away.
Shall we? He committed himself rather recklessly because he didn't really have much time.
Would this new battery be strong enough to reveal what potash was made of?
Working at top speed, he tries various ways of applying the charge.
Davy first tried putting a current through a mixture of potash and water. All that did was split the water into hydrogen and oxygen.
Do you see anything?
Leaving the potash unaffected.
And then he tried with dried potash. And again, nothing happened.
Finally, he moistened the dry potash just a bit before applying the electricity.
Dry potash won't conduct electricity, but when I added a little water and applied a strong electrical current, I soon observed a vivid action. There was a violent effervescence and small globules.
It sweats forth these glowing, shining globules.
They have a metallic luster, very much like mercury, and some of them exploded and burnt with a bright flame. These globules were the substance I had been searching for.
And this is a new element, in fact. It's potassium, one of the crucial elements for life, and he's discovered it. There's a wonderful description made by his assistant, who was actually Edmund Davy, a young cousin. He said, the professor became a boy again.
When he saw those globules of potassium burst through the crust of potash and catch fire, he couldn't contain his joy. It was some time before he could compose himself and continue with the experiment.
And you get the sense of this huge excitement, doing things under pressure, not quite knowing what will happen, whether the damn thing will explode. And then suddenly the unknown reveals itself.
The atoms of potassium and oxygen, so firmly glued together, could be separated by an electric current in the same way as those oxygen-hydrogen atoms in water.
The very next day, Davy used the same method to pull apart caustic soda, or lye, to reveal another new element, sodium. These two new metals were so soft they could be cut with a knife, and so eager to recombine with oxygen that they gave Davy the perfect demonstration for his next lecture.
Are you ready for anything? All right.
Davy had turned electricity into a powerful tool in the search for new elements. The year after discovering potassium and sodium, he used his battery to isolate 4 more elements, and chemists all over Europe seized on his technique, sending the number of elements even higher.
Sometimes the progress of science is due less to our intellectual powers than to the tools at our disposal. Nothing promotes the advancement of knowledge so much as a new instrument.
Exciting as these discoveries were, in time it would become clear that Davy's greatest contribution was his insight into one of the biggest questions in chemistry.
Somehow, the particles of matter have to be glued together to form molecules, and it was a complete mystery as to what this glue might be. What Davy has had, in effect, is a big idea.
If electricity could pry apart the atoms in water, potash, and soda, might electricity be the force that stuck those atoms together in the first place?
Is electricity an essential property of matter?
Perhaps electricity, with its plus and minus aspects, could be this kind of glue.
In every case that we know of, substances that combine with each other have opposite electrical states. And perhaps this is the reason they're attracted to each other, because opposites attract.
It looked as if electricity might play in chemistry the sort of role that gravity played in Newtonian physics.
Remember, he thinks of himself as on a par in some way with Newton. He's going to be the Newton among chemists. And in a sense, he does eventually achieve that.
In the 18th century, electricity was mostly parlor tricks, like making somebody's hair stand on end and attracting little bits of paper and so on. Davy showed that electricity is a fundamental aspect of matter. Electricity is what holds us together. It is the glue that links the particles of matter. And therefore, instead of being rather a side thing, electricity is going to be one of the really central features of science.
It would take more than a century for other scientists to figure out electricity's role. But after Davy, there was no doubt it would be one of the keys to solving the mystery of matter. Next time on The Mystery of Matter.
He figures out something rather extraordinary about the elements.
The eye is immediately struck by a pattern, a regular change in the horizontal rows and the vertical columns.
He had discovered an absolutely fundamental principle of nature.
My mother made her measurements over again, 10 times, 20 times, until she was forced to accept the results.
I proposed a new term to define this property of matter: radioactivity.
Major funding for The Mystery of Matter Search for the Elements was provided by the National Science Foundation, where discoveries begin. Additional funding provided by the Arthur Vining Davis Foundations, dedicated to strengthening America's future through education, and by the following. To learn more about the search for the elements and watch bonus videos on the featured scientists, visit pbs.org/Mystery of Matter. The Mystery of Matter Search for the Elements is available on DVD. To order, visit shoppbs.org or call 1-800-PLAY-PBS.
Joseph Priestley was the first to publish his discovery of the remarkable gas we call oxygen. Antoine Lavoisier was the first to understand its true significance. But there's a third man in the oxygen story, a Swedish apothecary named Carl Wilhelm Scheele,
who's also, like Priestley, a wonderful experimentalist. In fact, he made the discovery before Priestley did, possibly as early as 1771.
But when he discovered the gas he called fire air, Scheele decided to publish his results in a book and waited years for his mentor to write the preface.
The book doesn't get published till 1777, by which time all the chemists of Europe had already heard about Priestley's and Lavoisier's work.
While Scheele's discovery of oxygen had no impact on the course of science, he did go on to have a hand in the discovery of 4 more elements.
And got zero credit for this. First of all, he was a pharmacist, and nobody paid any attention to him. Second, he was working in Sweden, and most of the scientific world paid zero attention to what was happening in Sweden. And third, he had the misfortune to die rather young as a result of his own experiments. He was constantly sniffing terrible chemical substances and was eventually found dead at his desk with so many toxic materials around him that to this day nobody has any idea exactly what he died of.